Hello, and welcome to 123 AP Physics with Zach Speaks the Science Geek. This week we're doing electrostatics and circuits. I know in the last video I said that I was doing simple harmonic, but I decided to skip that, and I'll be coming back to that next week. This week, electrostatics and circuits. Okay, so electrostatics, there's one formula that you're going to need to know, and that's K times Q1 times Q2 over R squared. K is 9 to the 9th. It's known as Coulom's constant. Q1 and Q2 are the charges of the two objects. This formula is the formula for calculating the attractive or repulsive force between two electrically charged objects. So Q1 and Q2 are the charges. They're measured in coulombs. 1 coulomb is actually a really big charge. So if you're seeing things like 10 coulombs, that's like you're going to be getting huge numbers, and that's why, because coulomb is just a big unit. And then R squared is the distance between the two squared. It looks similar to the gravity equation because it basically is the gravity equation, just with a different constant, and it's not mass that factors into electric charge, it's charge factors in. The important thing to note with electrostatics is opposites produce an attracting force and like repels. So opposites attract is true in electricity. So if you have two positively charged, even though they're going to repel each other. So you just have to remember that. This formula won't tell you if it's attractive or repulsive. It will just tell you the magnitude. Okay, so induction and conduction. This is the other part of electrostatics. Induction, it's when an electrically charged object is brought close to an unelectrically charged object, but they don't touch. And so the electrons in the uncharged object are attracted to the ones in the charged object, but they can't jump across. Whereas conduction, they do touch, and so what happens is the electrically charged object, its charge is halved, and it crosses over into the uncharged object. And the uncharged object can be charged. I shouldn't be saying uncharged. It's usually uncharged, but it can have a positive or a negative charge. Induction is usually one's uncharged, but conduction, they might be charged. And so what happens with conduction is the sum of the charges is halved, and that's the new charge for the two objects. If there are three objects that are all touching at once, then the sum of the charges would be divided by 3. It's the average. It averages the charges. And again, you have to remember negative and positive charge. Those would be different. Okay, so circuits. The three main things in circuits in terms of units is voltage, resistance, and current. Voltage, or the electromotive force, EMF, is represented by a V, and it's kind of the force that pushes the electrons along the circuit. Resistance, R, the material's resistance to the electrical current. It has a formula of its own. You won't use it much in Physics 1, but it's there if you need it. It's phi L over A. So that's the length of the material over the cross-sectional area of the material. And then current is the number of electrons passing through a substance per second, or the it's a representation of that. It's like coulombs per second, I believe is the proper unit. That's measured in amps. Resistance is measured in ohms. Voltage is measured in volts. And so the main formula is what's known as Ohm's law. It's V equals IR. Ver is how I remember it. So the voltage is equal to the current times the resistance. And then so conservation of charge is charge is conserved through a circuit. So the electrons don't just mysteriously get destroyed. The voltage is lost, but the electrons aren't. And so this is a series, okay? Imagine these are resistors or something. They're in series, they're a direct line. and then these two are in parallel. See how the objects are parallel to each other? Okay, so because of conservation of charge, if you're going through a series, the current through the entire series will be the same. And also because of conservation of charge, if you're going through parallel, the current has to be split, but it's still going to add up to the original. So the voltage drop across parallel is always going to be the same. So if this were 3 ohms and this were 2 ohms, this would get 2/3. This would get, and say there were 5 amps of current, this would get 2, this would get 3, and that way you both get a drop of 6 volts across. Whereas here, if this were 2 and this were 3, there'd still be the 5, so this would be 10 and this would be 15. So, just important to note, you're going to be using these two rules a lot. That current through series components is equal and voltage drop across parallel components is equal. So resistors. If you got a bunch of resistors in series, to condense them, you just add them all up. It's pretty simple. If the resistors are in parallel, you have to do what's called the harmonic mean, and so that it's 1 over the equivalent resistance is equal to 1 over the first resistance plus 1 over the second resistance for all the resistors. And you'll find out that if the resistors have the same resistance, and there's 2, the resistance is going to be half the resistance of just 1. If there were 3, the resistance would be 1/3 of just 1. And with parallel, the total resistance is always going to be less than the individual resistances. You're also going to be needing that to condense resistors. Okay, so the components of the circuit. There's a resistor, which is a squiggly line. That's how it's represented. It looks kind of like that right here. This R1. That stands for resistor 1. Just a squiggly line. A wire is just a thin line. So right here, these are all wires. A battery is 2 lines like this, or sometimes it can be 4 lines. They'll be parallel though. And then ammeter and voltmeter. An ammeter measures current, and it's a circle with an A in it, and they're always in series with the circuit. And the voltmeter measures voltage drop, and it's in parallel with what you're measuring the voltage drop across. Ammeters have very low resistance, so if you run too much charge through them, you can blow them out. And voltmeters have very high resistance. An ideal ammeter would have 0 resistance, and an ideal voltmeter would have infinite resistance, and that way no current would go through it, and all the current would just go through the object that you're trying to measure. Interesting to note, just remember that ammeter is in series, voltmeter is in parallel. Okay, to solve a circuit, you're going to find the equivalent resistance of the circuit. If you know what the battery's voltage is, you're going to find the current. If you know the current, you're going to find the battery's voltage with V equals IR. And then you're going to find the voltage drop across each component of the circuit. That's what solving a circuit means. Sometimes you'll be asked that. Sometimes you'll just be asked, what is the voltage drop across the first resistor? But you still have to do those first 2 steps so you know the current through the circuit. Okay, power. The formula for power is P, power, in watts, is equal to VI, the voltage times the current. You can use V equals IR to rearrange that. You can get V squared over R. You can get I squared R. They're all the same thing. They're all just different ways of measuring power. And the thing about power is more power equals a brighter light. You'll often be asked, if the lights are hooked up in parallel or in series, when are they brighter? And the answer is always going to be parallel, because there's less resistance, which means more current, which means brighter lights. Okay, so the first problem. An object with charge 0.5 coulombs is placed 0.1 meter away from an object with charge 0.2 coulombs. what is the magnitude and direction of the force between the two? So here we're going to be using that first formula we saw. And in one's direction too, so we have to remember, like repels, these are the same, so they're going to be directed away, the force is going to be directed away from them. And so we'd say that K times by 0.5 times by 0.2 divided by 0.1 squared is about 9 times 10 to the 10th newtons and away from each other. So see what I was saying about how coulombs are a big unit, and you're going to get a lot of charge if you've got a good, if you got half or a quarter of a coulomb, you're going to be getting a lot of force between the two. 9 times 10 to the 10th newtons. That's 9. Hold on. 100, 100,000, million. So that's 9 billion newtons. 9 billion newtons. 100,000, million, 100 million, 100 million. Yeah, 9 billion newtons. That's ridiculous. We usually work with like 100 newtons, or at most like 120 newtons. Now we're working with 9 billion, so you could never get this to work in reality. They'd be so repulsed by each other that you'd never be able to place them 0.1 meter away from each other. Okay, problem 2. So this is our first circuit. In the circuit above, a 12-volt battery is connected to 2 resistors with a resistance 5 ohms and 12, that should be ohms. What is the equivalent resistance? What is the current? What is the power? Okay, so first thing we do is find the equivalent resistance. They're in series, so we just add them up. It's 17 ohms. Okay, equivalent current. So 12-volt battery, so V equals IR, so V over R equals I, so 12 over 17 equals about 0.7 amps. What is the power? So we know V, we know I, we know R, so we can use any formula. In this case, I used V squared over R, and so I said that 12 volts squared over 17 ohms is equal to 8.5 watts. Alright, pretty easy problem. Moving on. A 24-volt battery is connected to 2 48 ohm resistors in parallel. So R1 and R2 are both 48 ohms. Power, resistance, current. So first we're going to find resistance. So we'd say that 1 over R is equal to 1 over 48 plus 1 over 48. So that's 1 over 24 is equal to 1 over R, right? Because 2 over 48 is 1 over 24 if you reduce the fraction. So then 1 over 24 is equal to 1 over R is equal to 1 over 24, so the resistance is 24 ohms. It's halved. 2 of the same is equal to half of an individual when they're in parallel. Okay, from that we can find the current, so 24 volts over 24 ohms is equal to 1 amp, and then we can do 24 volts, and so 1 amp is equal to 24 watts. Okay, FRQ. This one I got from the 2015 Physics 1 exam, so, and this was one of the harder problems. In 1 second to fewer, some students want to know what happens in the incandescent light bulb when it's in series with the resistor, current, energy, or both. They come up with the following 2 questions. What gets used up? Current, energy, or both? So do fewer electrons enter the bulb than leave the bulb? Leave the bulb than enter the bulb, rather. Does the electric potential energy of electrons change while inside the bulb? So that'd be voltage. Electric potential energy is voltage. That's all the stuff they have. Describe an experimental procedure that could be used to answer questions 1 and 2 above. Explain how the data could be used. And test if the light bulb is non-ohmic. So that means Ohm's law doesn't apply and the resistance changes as a function of current. So the first thing I do is I'd measure the current before and after, and so I'd have an ammeter and an ammeter on both sides of the light, and then I measure the voltage drop across the light. So that's my really crude diagram. It's kind of annoying to draw objects with shapes in PowerPoint. So I'd use the battery to send out different amounts of voltage. and I measure the ammeter and voltmeter readings. If the ammeter readings differ, charge is not conserved. And then if the voltmeter, sorry, that should be voltmeter. I'm not sure why I wrote ammeter. If the voltmeter reading is not 0, then there is a voltage drop. So we'd expect that the charge is conserved and that there is a voltage drop. So, okay. And then to measure if the light bulb is non-ohmic, we'd remove the voltmeter and use an ammeter, and use the ammeter reading to determine resistance with varying voltages. So we'd say V over I. If resistance is not constant, light bulb is non-ohmic. And then the sources of error would be the ammeters can be read incorrectly. We don't have ideal ammeters, so they do introduce some resistance. It may be broken. They're broken easily. And like if you have a broken ammeter, you might not know that it's broken, and so that introduces a source of error. That's all for this week. Next week is going to be the last video. We're doing simple harmonic motion and waves. So see you then. Bye.